So let's look at some applications and why we were going to use these and why we look at these. Basically, the three functions that we looked at, which are the ramp, the unit step, and the unit impulse, these are useful when we're talking about with respect to switches. Okay, so we can create these signals by flipping a switch, so I'll say that. So let's take a look at this one here. Say we've got a circuit that looks like this, and we've had stuff like this before. You know, say we've got we're going to go to A and B. And we'll say that this is a switch that is flipped at t equals 0. Okay, so that's one way to write it. I'm going to say, okay, well, this is V naught. Like that. Now, another way to write it would be to say, well, that's the same thing as saying that we've really got this here, just like this, but now instead of labeling that V naught, what I'm going to do is I'm going to label it V naught UT. So basically what I've said is that at time equals 0, I'm going to flip that switch, because essentially what do we have is I have, well, that V naught of UT is going to be equal to 0, right, for time less than 0, and it's going to be equal to V naught for time greater than 0. So whenever I flip the switch, it's, remember, at time greater than 0, U of t is 1. So that would be V naught times 1, which is V naught, which is what I've got here. So that's where that's coming from. Just the idea that I can now write my voltage in terms of the unit step instead of having to go through all the trouble of drawing in that switch. And so that's very, very useful. And then another application that we're going to use these for is in sampling. And we also call it sifting. All right. And we're going to use this with the unit step, with the unit impulse. I mean, we're going to look at this. This is an application of the unit impulse. Okay. So I want you to consider a function, just some miscellaneous function f of x. We'll call it f of t. Okay. So we have this function, and we have our other function, our one area under the curve E function occurring at some position in time, some t naught. Okay, here's a question. Now this isn't 1, so let me try this again. If I wanted to multiply f of t, and this is going to be delta t minus t naught, right, because it's shifted to the right, t naught, so flipped and shift. I can't actually multiply these together, right, because this is undefined. So I can't just say, well, what is f of t times that? But what I can do is I can integrate it. I can integrate multiplying them together, which just sounds really awesome. And that will give me the area of the curve. So what would happen if I kind of tried to sketch this out? If I multiply this part times the equivalent part over here, it would be 0, right? Because this is a 0, 0 way. So I'm going to mark t naught here. So anything before t naught that I multiply by f, I'm just going to get 0, right? Because 0 times, because these are all 0, so zeros times any of this is just going to give me 0. And the same thing on the right. 0 times any of this is just going to give me 0. Like that. Now for the instantaneous craziness that I multiply this times this, I'm going to get that impulse function. I'm going to get, it's kind of like a 1, but it's not exactly. But it's going to be f, now what's f at this specific point is going to be f of t naught times t minus t naught. or really just f of t naught. I'm just going to say it like that. It's going to have a height. One way to think about it is it has a height of f of t naught. What it really means is that the area, and we can't just say that because, remember, this is infinitely tall, but has an area under the curve of 1. That's what we said. Has an area under the curve of 1. So we can't just, just outwardly say, oh, this is just a line that comes up to f of t. What you really want to think about is it's the area under the curve, and, if I was going to evaluate an integral from, say, here to here, if I was going to add, that's not the area of the curve, but the area of the curve is 0, 0, 0, f of t naught, 0. And that would be my area of the curve. So again, 0, 0, 0, f of t, plus f of t naught, plus all these zeros. So my area under the curve from A to B of f of t naught times this sampling function is going to be f of t naught. And this is going to look really, really weird. So, but basically the idea again is that we're just going to sit along here, and if I'm going to integrate from any A to B, as long as it includes that t naught in the middle, then I've got bloom, 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 bloom. And then here's my, remember, the area under the thing before was a 1, and now I'm just scaling it by f of t naught. And then here's some more zeros under the curve that I'm adding together. And so if I have, 0, 0, 0 plus f t naught plus lots more zeros, well, I'm going to finally end up with f of t naught. Okay? So that's a very useful thing because you'll have a signal. I mean, how you would use this is you have a signal going through and you're like, I want to pull off parts of this signal. Well, I'm going to integrate it with this unit impulse is really what's going on. So when you have equations, for example, like you have examples, if I wanted to integrate 0 to 10, and this is a lovely little example of something that looks really hard and is at least practically very, very simple to solve. If I have this function multiplied by this unit impulse, really what I'm saying is, okay, I have this graph, whatever this graph looks like, and really what I want to do is I want to sample it at time equals 2. So really the simple way to answer this is to say, I'm going to take this, I'm not even integrating it, I'm just actually taking the function and evaluating it at t equals 2 to get whatever 4 plus 8 minus 2 is. 10? 10. 10. Okay. Now about the only way they could throw you is to say, okay, well what if we evaluate the integral from 10 to 4, 4 to 10, and try to do the same thing. And I want to integrate, I want to sample it at t equals 2. Well, that would be like saying, okay, so I've got this parabola, whatever it looks like. I don't know. I'm just terrible at those. I can't ever think of them. And I want to sample it at t equals 2, but I only want to integrate from 4 to 10. So I'm only integrating in this section. Well, since I'm just sampling it, remember that it's only non-zero at that one point. It's only non-zero at that one point. So if I'm integrating from 4 to 10, the area under the curve is just flat out going to be, thank you, the area under the curve is just flat out going to be 0. So that's about the only thing I can do to freak you out. So it's 0 because 2 is not between 4 and 10. So that's useful. Some other things to remember just as you're going through this as well. So remember, as you're solving the problems, that your unit step is your derivative of your ramp. So therefore, your ramp is equal to the integral of your unit. And your impulse is equal to the derivative of your unit step. So therefore, your unit step is equal to the integral of your impulse. And that should be enough to kind of get you started on these problems. Just remember, if you need help with the shift, stretch, flip, transformation stuff, You know, there's that college algebra lecture video available, and I won't know if you watch it. There's no shame. I haven't seen it. Well, I had to look it up whenever I taught it again for college algebra. Just something you need to be good at and make sure that you're really confident with that and comfortable with this moving forward.